Hello viewers, welcome to the present episode on periodic properties. In the previous lessons, we learned about the trend in trend in electron affinity and determination of electron affinity with the help of Born-Haber cycle. As well as we learned about the electronegativity, what is electronegativity and how it is determined. In the present lecture, we will learn about the factors affecting the magnitude of the electronegativities, then periodicity in the electronegativity in the periodic table, then application of the electronegativity, as well as we will learn all these detailed we will summarize in the periodic trends. What are the main factors which affect the magnitude of the electronegativities? There are number of factors on which the value of electronegativity depends, but the main factors on which it depends are size of atom, then effective nuclear charge. It also depends on the oxidation state of the atom or the ion. Then it depends on the hybridization of the central atom, as well as finally it depends on ionization energy as well as electron affinity. So, the first factor on which the value of electronegativity depends is the size of the atom. We have seen also that the small atom has more power to attract the shared pair of electron. Therefore, a smaller atom has greater tendency to attract the shared pair of electron towards themselves than the larger atom. Hence, a smaller atom has high value of electronegativity than the large atom. So, it depends on the size of atom. Then it depends upon the effective nuclear charge. We have seen in the periodic table that the nuclear charge increases when we move across the period or when we move down the group, but it depends solely on the effective nuclear charge, and the effective nuclear charge, therefore, this electronegativity of an atom is proportional to the magnitude of the effective nuclear charge. Higher the magnitude of effective nuclear charge, higher will be the electronegativity of the atom. And the higher magnitude of effective nuclear charge is when the small atom is small and it has high nuclear charge, then it has high effective nuclear charge. Therefore, atoms having higher effective nuclear charge has high value of electronegativity. Then a very important factor on which the value of electronegativity depends is their oxidation state. We know well that size of cation is always smaller than its parent atom, whereas size of anion is always larger than its parent atom. So, the size of cation decreases with increase in their oxidation states. We know in case of iron, we take the example of iron, it is present in +2 oxidation state, iron is also present in +3 oxidation state. +3 oxidation state, it has the smaller size than in +2 oxidation state than in the atomic form iron. So, the size of iron varies from or decreases from Fe to Fe +2 then to Fe +3. So, in this order the size of iron decreases, or we can find out that depending on the oxidation state, size of the atom is decreasing or size of the ion is decreasing. So, we have just seen that smaller is the size of the atom or cation, greater is the value of electronegativity. Therefore, since Fe +3 ion is the smallest in this particular series, so this Fe +3 has the highest value of electronegativity, then Fe +2, and Fe +2 in turn has high value of electronegativity than Fe. So, in this here we see that the electronegativity of Fe is 1.8, whereas that of Fe +2 is 1.83 and Fe +3 is 1.96. So, in this way, with increase in oxidation state of the cation, the electronegativity of the cation is also increasing. This we can take with another example of chlorine. Chlorine is present in different molecules in different oxidation state, and for example, this chlorine if present in HClO, then its oxidation state is +1, and if we take the compound HClO3, then the oxidation state of chlorine is +5. Here we also see that since the oxidation state of chlorine in HClO3 is +5, so this chlorine atom in HClO3 has high value of electronegativity than in HClO, where it has an oxidation state of +1. Similarly, as I have already said that the size of anion is also larger than its parent atom. So, in case of anions, we find tendency to attack the shared pair of electron decreases with increase in size of the anion. For example, the size of anion in case of fluorine atom and the fluoride ion, the size of fluorine atom is smaller than its fluoride ion. Therefore, the value of electronegativity of fluorine atom is 4, whereas that of fluoride ion is 0.8 only. Because in case of fluoride ion, size is increased, and due to increase in size, the tendency to attract the shared pair of electron decreases. Therefore, in case of anions, the electronegativity value of electronegativity decreases with increase in charge. So, this is a very important factor to determine the value of electronegativity. Then another important factor to determine the value of electronegativity, or on which the value of electronegativity depend, it's the hybridization. And we know that during hybridization, number of orbitals of almost comparable energies redistribute their energy to give rise to different orbitals of equal shape and energies. But we know that during the process of hybridization, s orbital, p orbital or d orbital will mix to form new hybrid orbitals. And these new hybrid orbitals, depending on the percentage of the s character in them, the value of electronegativity varies. So, the hybridization also affects the electronegativity values. Since s orbital has highest penetrating power, it is nearest to the nucleus. Therefore, electrons, if the hybrid orbital has more s character, then that atom will have high value of electronegativity. So, due to this, it has greater tendency to attract the electron if it has more s character, high value of electronegativity. For example, we take the case of carbon. Carbon in case of methane, CH4 is present in sp3 hybridization. Carbon in ethine, C2H2 is present in sp2 hybridization. Carbon in C2H2 is present in sp hybridization. In these three hybrid orbitals, or in these three cases, it is sp3 hybridized, sp2 hybridized and sp hybridized. And in sp3 case, s character is only 25%, whereas in sp2 the s character is 33%, and in sp hybridized orbitals s character is 50%. So, in this way we find that the percentage of s character increasing from sp3 to sp hybrid orbitals, and with this increase in percentage of s character from sp3 to s orbital, we find that the carbon atom in these compounds have different values of electronegativity. So, carbon in case of, here we find that carbon in case of methane CH4, it has 2.53 value of electronegativity, because here the s character is 25%, whereas in C2H4 ethine, it has s character is 33% and the electronegativity of carbon is 2.75, whereas in case of C2H2 acetylene, it has 50% s character, its value of electronegativity is 3.3. So, in this way we see here value of electronegativity depends also on the hybridization. Then next important factor on which electronegativity depends, its ionization energy and electron affinity. We have just seen in the previous lectures that the value of electronegativity according to Mulliken is an arithmetic mean of ionization energy and electron affinity. It means those atoms which have high value of ionization energy and high value of electron affinity will naturally have high value of electronegativity. and this ionization energy is the amount of energy required to remove an electron, whereas electron affinity is amount of energy released when an electron is added. So, if they have high value, naturally they will have high value of electronegativity. And if we see that 17th group elements or the halogens which have high value of ionization energy and high value of electron affinity, therefore, they have highest value of electronegativity. Similarly, on the left side in the periodic table, alkali metals are there which have very low value of ionization energy, which have very low value of electron affinity, therefore, they have least values of electronegativity. So, here we find that value of electronegativity also depends on ionization energy as well as on electron affinity. So, these are the factors on which the value of electronegativity depends. Now, we see how the value of electronegativity varies in the periodic table or the periodicity in electronegativity. If we see this variation in the value of electronegativity, we will see these variation in S block and P block elements. So, we find that the value of electronegativity decreases when we move down the group, whether it is a S block element or it is a P block element, whether it is alkali metals or halogens or oxygen block elements or carbon block elements, we find that when we move down the group, the value of electronegativity gradually decreases, and this decrease in value of electronegativity is due to increase in size. When there is an increase in size of the atom, the number of electrons increases in the inner shells, and the increase in number of electrons in the inner shell causes the increase in screening constant values and decrease in effective nuclear charge. So, due to increase in screening constant value and decrease in effective nuclear charge, the number of shells increases, therefore, the value of electronegativity decreases with increase in size. That when we move down the group, the value of ionization energy also decreases and the value of electron affinity also decreases. These values again depends on number of factors, and these all factor leads to decrease in value of ionization energy and decrease in values of electron affinity. And with this decrease in values of ionization energy and electron affinity, naturally the value of electronegativity also decreases when we move down the group. And when we move along the period, we see that size of atom is decreasing. When we move along the period or across the period, we see that size of atom is decreasing, and this decrease in size because the electrons are added into the same shell, and due to electron added into the same shell, the screening constant remains almost the same, whereas there is increase in effective nuclear charge, and due to this increase in effective nuclear charge, the value of ionization energy increases, the value of electron affinity increases, and with the increase in values of ionization energy, increase in value of electron affinity and decrease in size of atom, the value of electronegativity across the period increases. So, this is the periodicity in the value of electronegativity, and this value of electronegativity we can also see in the form of the periodic table. So, in this periodic table, when we move down the group, here we have shown only the halogens or the 17th group elements, fluorine, chlorine, bromine, iodine, and here we see that what are the electronegativities of these halogens. The electronegativity values of fluorine is 4.0, chlorine is 3.0, bromine is 2.8, whereas iodine is 2.6. Here we find that there is a decrease in value of electronegativity when we are moving down the group or when we are going down the group. So, this when we go down the group, as it is just I have explained that there is a increase in radius of the atom, there is increase in number of shells, there is increase of the screening constant or screening value, the effective nuclear charge is decreasing. Therefore, the values of these atom, the electronegativity value is gradually decreasing. Similarly, when we move across the period or when we go across the period, here we find the second period element: lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. And here we find that the values of these values of electronegativity is gradually increasing. For lithium it is 1, beryllium it is 1.5, boron it is 2, carbon 2.5, nitrogen 3, oxygen 3.5 and fluorine it is 4. So, this value is increasing because the size of atom is gradually decreasing. There is decrease, electrons are being added into the same shell, and due to this the forces of attraction is increasing, and with the result, when we move across the period, the value of ionization energy is gradually increasing. Now, this is again a very important figure. Here the values of electronegativity is shown in graph. Here we find that electron negativity value of fluorine, it is maximum, it is present at the peak, and we have just seen that the value of electronegativity of fluorine is 4. Gradually it is decreasing and halogens are present at the peak, whereas helium, neon, these are the noble gases which are present at the bottom. They have least value of electronegativity, they do not attract any shared pair of electron, therefore they have least value of electronegativity. And alkali metals are present just when we move in the graph towards the peak. So, here lithium, potassium, sodium and potassium. So, these are the values of electronegativity along with increase in atomic number. Now, to predict the nature of the bond, whether the molecule is polar or non-polar. Polar means it may be ionic, because, or if non-polar, then it is purely covalent bond, and purely non-polar molecule or the purely covalent molecule is one in which the shared pair of electron is present at the center of the nuclei of the two atoms. So, if it is present in the center, then the bond is 100% pure covalent bond, which is present only when the two atoms are similar, that is in homonuclear diatomic molecules. But if the atoms are different, then some polarity will be there, and due to that polarity, shared pair of electron will be shifted towards the one atom. So, if the difference in the electronegativity of the atoms A and B, that is chi A and chi B, the difference between electronegativity is 1.7, then bond is 50% ionic and 50% covalent. If the difference is more than 1.7, then higher will be the ionic character. If the difference is less than 1.7, then more will be the covalent character. So, with the difference in the values of electronegativity, we can predict whether bond is higher towards the ionic in nature or it is towards the covalent in character. But if it is the difference is 1.7, then it is 50% ionic and 50% covalent. Then a very important application of this electronegativity is the diagonal relationship shown by the elements. So, diagonal relationship is this, that when the elements present in next period and next group, they show similarities in the properties. Their physical as well as chemical properties shows similarities, and this similarities is known as diagonal relationship. In this way, lithium belong to first group, it shows diagonal relationship with the magnesium, which is member of third period and second group, or beryllium shows the diagonal relationship with aluminium. Similarly, boron shows the diagonal relationship with silicon, carbon shows diagonal relationship with phosphorus. So why they shows diagonal relationship? Here we find that the electronegativity value of lithium, that is 1, and magnesium is 1.2, which is nearly same. If the values are nearly same, then they shows similarities in their properties, and this similarity in property is known as diagonal relationship. Here in case of next element beryllium, we find its value is 1.5 and that of aluminum is also 1.5. Since their values are identical, this shows that their sizes of the atoms are almost same, and due to this they have almost same properties, same ionization energy value, same electron affinity value. Therefore, they shows relationship. So, this relationship is known as diagonal relationship, and it is depends directly on the property of the electronegativity, which is almost have identical values. Then the next application is the bond angles. If the electronegativity of central atom is less in polyatomic molecules, less will be the magnitude of the bond angle. Electronegativity of the central atom is less. Here we find that in case of nitrogen fluoride, trifluoride NF3, here the electronegativity of nitrogen central atom is 3 and the bond angle between nitrogen and fluorine is 102 degree. So, this bond angle is high. Whereas, if we move down the group nitrogen to phosphorus PF3, here we find that electronegativity of phosphorus is 2.1 and the bond angle is 97 degree. Then in arsenic trifluoride, electronegativity of arsenic is 2.0 and bond angle is 96 degree. In case of antimony trifluoride, electronegativity of antimony is 1.9 and the bond angle is 88 degree. So, here the lesser the electronegativity of the central atom in polyatomic molecule, lesser is the magnitude of the bond angles. In case of nitrogen trifluoride, it has high value of electronegativity, therefore, bond angles are more, because the shared pair of electron between nitrogen and fluorine, it will be shifted towards the nitrogen, and if it shifted towards the nitrogen, the bond angle will increase. But if it will be away from the central atom or towards the fluorine atom, then they can approach nearer to each other, and due to this approach there is a decrease in bond angle. So, this value of electronegativity we apply to the bond angles also, or with its help we can explain the bond angles observed in different molecules belonging to a particular groups. In this way we learned about the electronegativity. Now, as we have gone all through these periodic properties, we have seen the size of atom, we have seen the ionization energy, electron affinity, electronegativity. So, all these properties now can be summarized, and here we say that when we move across the period, here we are moving across the period. So, the size of atom decreases, atomic size decreases. Then when we move across the period, the electronegativity value increases, shielding effect is almost constant, ionization value is increasing, and electron affinity value also increases when we move along the period. Whereas, when we move down the group, we find that atomic radius is increasing, electronegativity value is decreasing. Due to large size, the force of attraction decreases, therefore, tendency to attract the shared pair is decreases, with the result value of electronegativity decreases. Then the shielding effect is increases, because number of shells increasing and the number of electrons in the inner shell is increasing. This results in increase in shielding effect, and there is decrease in ionization energy when we move down the group. Because of number of factors it depends, and all these factors favors the decrease in value of ionization energy. Again, the value of electron affinity also decreases when we move down the group. So, in this way we have seen these are the properties, various properties which shows periodicity in their property. So, in this present chapter we learns about the factors affecting the magnitude of electronegativity, and the various factors which affect the magnitude of the electronegativities are oxidation state, then hybridization, size of atom, effective nuclear charge, ionization energy and electron affinity. So, all these factors affect the magnitude of the electronegativity. Beside this, we have also studied about the periodicity in the electronegativity and its application. The applications are particularly used to predict the nature of the bond present between the atoms, or this can be applied to explain the bond angles observed in the molecules. So, these are the very important applications of the electronegativity, and finally, we summarized all the trends right from the lesson 1, where we have studied about the size of atom, then ionization energy, ionic size, electron affinity, electronegativity. So, how these varies in the periodic table. Usually the ionization energy, electron affinity, electronegativity increases, whereas size of atom decreases when we move across the period, and when we move down the group, the value of ionization energy, electron affinity and electronegativity decreases, whereas the size of atom increases. This is the general trend we observed. Beside this, there were number of exceptions which were explained at the proper places. So, in this way we have read about the periodicity in periodic table, or we have learned about the periodic properties. Thank you.